The insulation in your walls will fail. Not because anything went wrong, because it was designed that way. Right now, behind the drywall of the average American home, there are rolls of compressed glass fiber, pink, fluffy, made in a factory by a company that generates $9.7 billion in annual revenue. That insulation was rated for 30 years when it was installed. Today it has compressed by somewhere between 15 and 30% of its original thickness. The air pockets that gave it its R value are collapsing. When it reaches 50% compression, which it will, it loses roughly 20% of its insulating capacity. You will not know this is happening until your energy bills climb and a contractor tells you the walls need to be redone. In 1903, a family in alliance. Nebraska built a house. No fiberglass, no spray foam, no contractor. They used the stalks left in their fields after the wheat harvest was done, pressed into blocks, stacked into walls, plastered with lime. That house is standing right now, 121 years later. The insulation has not been replaced. The walls have not degraded. An American federal laboratory has since tested what those Nebraska settlers built and produced a number, R30. For grain stalks, for something that grows back every single year, in every field in America, and currently retails for $3 to $5 a bale. Here is the only question that matters. Who decided that the $9.7 billion solution was the one that would go into your walls, and not the $500 one that outperforms it? By the end of this, you will know the answer, and you will understand that the answer was never about performance. This is the story of the insulation that cannot be monetized, and exactly what that costs you. Every week on this channel, we find another case, another technique, another material, another system that was working before the industry that replaced it convinced you it was primitive. Subscribe if you haven't. The next video in this series will cost you nothing to learn from. It will cost the industry roughly $2,000 in revenue for every person who watches it. The insulation industry wants you to believe the story begins in 1938, in a factory in Newark, Ohio, where a company called Owens Corning first produced glass fiber in commercial quantities. That is when insulation became insulation, in their version. That is when walls became properly sealed against heat and cold. Before that, the assumption goes people were just cold. The actual history starts roughly 10,000 years earlier. In Mesopotamia, the civilizations of the ancient Fertile Crescent were building with mud brick, and they had already solved the same problem that Owens Corning claims to have solved in 1938. Reed bundles, tightly packed, were wedged between structural elements. The hollow internal cavity of each reed stalk trapped air exactly the way straw does. The people who built the first cities understood, empirically if not theoretically, that bundled plant material slowed the movement of heat through a wall. They did not have the language of R values, they had the experience of sleeping through winter. The Roman builders who came later understood the same principle from a different angle. Their hypercost systems, the underfloor heating networks in elite villas and bathhouses, depended entirely on insulated wall and floor surfaces to work. The heat the hypercost generated would have escaped through the walls within minutes if those walls had not been thick, dense, and insulating. Roman engineers packed pumice and volcanic aggregate into wall cavities, layered hollow ceramic spaces beneath floors, and built with materials whose only job was to trap air and slow heat transfer. This is not coincidence. Every advanced civilization that dealt with thermal extremes arrived at the same engineering principle. Air, when trapped in small pockets and held still, is one of the most effective insulators available. The question was always how to trap it. And for most of human history, the answer was plant material. In medieval Europe, wattle and daub walls, the standard construction method for 90% of the population for roughly 1,000 years, embedded straw directly in the mud and lime mix that filled the structural frame. The straw was not a filler. It was the insulating matrix. It is why medieval houses, cold and drafty as our mythology about them tends to be, were significantly better at retaining heat than their size and fuel consumption should have allowed. The story arrives in America in the 1870s, on the treeless plains of Nebraska. And here is where it gets specific. The Nebraska sandhills are sand dunes stabilized by prairie grass, and they were being settled by homesteaders who had almost nothing to work with. No timber, no stone, no conventional building materials of any kind. What they had was an immense quantity of prairie grass, and starting in the late 1870s, a machine that changed everything. John Appleby, a Wisconsin inventor who had spent 20 years trying to mechanize the binding of cut grain, patented the automatic twine knotter mechanism in 1878. He was quiet about it in public and obsessive about it in private, and the machine he perfected made the mechanical grain baler reliable at scale. The baler was invented to solve a disposal problem. After grain harvest, the stalks left in the field were a nuisance. Farmers compressed them into blocks to move them more easily. And then, somewhere in a county in Nebraska in the mid-1880s, someone stacked those blocks into a wall. The first documented straw bale structures appear in Arthur County, Nebraska in the late 1880s. The settlers who built them were not conducting an experiment. They were solving a problem with the only material they had in abundance. And what they discovered, that first winter in those buildings, was something that should have rewritten the history of construction. The houses were warm, not just tolerable, not just survivable, genuinely warm. Warmer than the sod houses their neighbors had built, warmer than the wooden frames that would follow when timber became available. At -30 degrees Fahrenheit in winters that killed cattle and froze water pipes solid, the families inside straw bale walls were sleeping through the night without extra fuel, and cool in summer. The same walls that held heat out in December held heat out in July. The Nebraska farmers had, by accident and necessity, built the most thermally efficient residential construction method in America. Within a decade, there were dozens of these buildings across the sandhills, then more across Nebraska, Wyoming, and South Dakota. In 1903, a man built a house in Alliance, Nebraska. It is still standing today. 121 years. Same walls, same insulation, no replacement. That is the foundation, remember it. Because what comes next is the story of how an industry decided that foundation was inconvenient. Before we get to the suppression, which is a deliberate word for what happened, you need to understand why straw bale works the way it does. Because the physics is not complicated. And once you understand it, everything that follows becomes obvious. A straw stalk is not a solid fiber. It is a tube, a hollow cylinder of cellulose with an outer wall roughly 0.5 millimeter thick, and an air space running the full length of it. This is why straw is straw, and hay is hay. Hay, which is cut green grass, is solid, or nearly so. Straw, which is the stem left after grain harvest, is a collection of hollow tubes. When those tubes are compressed into a bale, 3 things happen simultaneously. The tubes themselves align roughly parallel, trapping air inside each one. The spaces between the tubes trap additional air, and the overall compression creates a dense matrix of tiny, static air pockets at 2 levels, inside the stalks and between them. Air, when it cannot move, cannot conduct heat efficiently. A 12-inch depth of these interlocked air pockets achieves when tested by a federal laboratory with guarded hotbox apparatus, an R value of between 26 and 33, depending on bale density. To put that number in context, the standard insulation installed in American walls, fiberglass batt in a 2x6 frame, achieves R19 to R21. Spray foam, the premium option that costs $8,000 to $15,000 to install in a house, achieves R20 to R24. Straw bale at its floor beats both. At its ceiling, it beats them by 65%. But here is where most people's understanding of straw bale stops, and where the misunderstanding begins. People hear the word straw, and they think of the 3 little pigs. Loose material, something that burns, something that collapses under load. A plastered straw bale wall is none of those things. The plaster is not cosmetic. It is structural. When lime plaster, earth plaster, or cement stucco is applied in a layer 2 inches thick on both faces of a bale wall, it creates what engineers call a stress-skinned panel. 2 rigid skins bonded to a dense compressed core. The structure is stronger in lateral resistance than a standard stud and drywall frame. This is why load-bearing straw bale construction, walls that carry the roof load directly, works at all. About the fire. This is the objection that comes first, every time, and it is the most thoroughly documented reversal of common assumption in natural building. A plastered straw bale wall does not burn. Intertek, one of the primary independent testing laboratories used for building code compliance in the United States, conducted a STME 119 fire tests on plastered straw bale wall assemblies. They subjected the walls to a standardized fire load at temperatures exceeding 1000 degrees Fahrenheit. The result? A 2-hour fire resistance rating. The standard wood frame wall with fiberglass insulation and drywall achieves a 1-hour fire resistance rating in the same test. The straw wall outperforms it by a factor of 2. Why? Because compressed straw covered in 2 inches of lime plaster has almost no oxygen access. The surface is mineral. The interior cannot be reached by flame. The only way to get a plastered straw wall to burn is to first remove the plaster, then expose the straw to extended flame and sufficient oxygen. A house fire does not provide those conditions. It provides heat and smoke. A plastered straw bale wall sheds both. The last thing to understand about how this system works is the breathing. Lime plaster is vapor-permeable. Moisture can enter, move through the wall, and exit. This is the opposite of spray foam, which creates a vapor barrier that traps moisture inside wall cavities, leading over decades to the mold and structural decay that contractors are called back to address. Straw bale walls, properly plastered, stay dry because they breathe. Moisture does not accumulate. It passes through. And the straw itself. Every stalk in every bale is agricultural waste. The leftover stem from wheat, rice, barley, or rye harvest. The grain is taken, the straw remains. American farmers currently burn millions of acres of it every year, creating visible pollution across the grain-growing states because there is no market for it. 1 acre of wheat produces 2 to 3 tons of straw bales, enough to insulate the walls of a modest home. It grows back next harvest, the same field, the same straw, every single year, forever. That is the material. That is the system. Now here is the question you should be asking. If this material outperforms fiberglass, resists fire at twice the standard, breathes, and grows back from agricultural waste every 12 months at $500 to $1,500 for an entire house compared to $3,000 to $15,000 for factory alternatives, why have you never been offered it? The answer has a name. The year Owens Corning was founded, 1938, was the same decade straw bale construction in America was quietly fading from practice. There is no memo, no meeting, no executive who decided straw bale must die. What there is, instead, is a system. And systems do not need memos. They just run. Owens Corning was born with government backing. Their first major contracts were federal military applications for fiberglass during World War II. By 1945, they had the production infrastructure, the regulatory relationships, and the capital to begin marketing aggressively to the civilian construction market. Fiberglass was industrial, modern, scalable. You could order it by the truckload, delivered on a schedule, in standardized rolls of known dimensions, at known R values, with known installation procedures that any carpenter could follow without special training. Straw bale required local sourcing, local knowledge, a regional supply chain that had to be rebuilt every time someone wanted to build. It did not fit the post-World War II construction model, which was about speed, standardization, and the ability for a large developer to replicate the same building on 1,000 lots in 100 cities. So the market chose fiberglass. Not because fiberglass was better, because fiberglass was systemically convenient. What came after was not active suppression, it was passive exclusion. And passive exclusion, operated long enough, produces the same result. The National Insulation Association was founded in 1953. Its membership consists of insulation manufacturers and contractors. Its activity includes participation in building code committees. ASHRAE Standard 90.1, the energy code that most American states have adopted as their minimum building energy performance requirement, sets R-value requirements for walls. Those requirements are written around conventional framing: 2x4 walls, 2x6 walls, standard stud cavities. The code has no category for a wall system 23 inches thick and made of compressed grain stalks. A straw bale wall must apply for classification as a non-standard system, requiring additional documentation, third-party testing, and engineering review that a standard fiberglass installation simply does not need. This is not a conspiracy, it is a filing system. But the outcome is the same. The International Residential Code added Appendix S, the straw bale construction standard, in 2015. That was 60 years after the modern straw bale revival began, and 130 years after the first straw bale houses were built in Nebraska. And Appendix S is non-mandatory. Each jurisdiction must adopt it separately. As of 2024, most jurisdictions in the United States have not, which means that a homeowner who wants to build with straw bale in most American counties must navigate a permitting process designed for materials the building official already knows, has forms for, and can process in 48 hours. The straw bale permit takes months, sometimes years. Sometimes it is simply refused. Then there is the insurance problem. State Farm insures more American homes than any other company. Allstate insures the second most. Farmers Insurance, the third. All three classify straw bale construction as a non-standard or unconventional building method. This triggers three possible outcomes: a premium increase of 15 to 40% above standard rates, a requirement for additional engineering documentation at the homeowner's expense, or an outright refusal to underwrite the property. The irony, which you have already understood if you were paying attention to the fire test numbers, is that they are charging more to insure a wall with twice the fire resistance rating of the wall they are comfortable insuring at the standard rate. It gets more specific. Fannie Mae and Freddie Mac, the two government-sponsored enterprises that guarantee the majority of American mortgages, maintain lending guidelines that effectively exclude unconventional construction. Lenders who want to sell loans on the secondary market, which is essentially all of them, must comply with Fannie and Freddie guidelines. A homeowner who wants a conventional 30-year mortgage to build a straw bale house cannot get one. They must find a portfolio lender, rare and more expensive, or finance it themselves. Strip away the code complexity, the insurance premium, and the mortgage unavailability. And what you have left is this: a building method tested by federal laboratories, passing fire tests at twice the standard requirement, practiced continuously in Nebraska since 1886, is classified by every financial institution that matters as a fringe, risky, unproven alternative. The data says it outperforms the standard. The system says it does not exist. And then there is the three little pigs. The story appears in its modern form in 1890. The first documented straw bale buildings in Nebraska were built in the mid-1880s. The timing is coincidence, but the cultural effect is not. For 130 years, the most widely taught story about straw as a building material has been the story of the straw house that blows down. Children learn this before they learn arithmetic. The straw house is the weak house. The brick house is the strong house. This is not industry propaganda in the organized sense, but when someone proposes straw bale walls, the first response is not a cost analysis. It is a story told before age 5. $9.7 billion a year. 130 years of non-mandatory building codes, insurance exclusions, mortgage unavailability, and a children's story. That is what stands between you and the best performing insulation in American history. At some point, the numbers start to speak loudly enough that even the systems designed to ignore them have to write them down. The vindication of straw bale construction did not begin in 2015, when the IRC finally added Appendix S. It began much earlier, and in a place that carries significant authority in American construction science. Oak Ridge National Laboratory is one of the most respected materials testing facilities in the United States. Established in 1943 as part of the Manhattan Project, it has since become the federal government's primary institution for energy and materials research. When Oak Ridge produces a number, that number is not disputed. When Oak Ridge tested straw bale wall assemblies in their guarded hotbox apparatus, applying known heat loads to measured wall sections and recording the thermal resistance with laboratory-grade instrumentation, they produced an R value between 26 and 33. The number that emerged from the most respected federal testing facility in the country was higher than any manufactured insulation product at standard installation depths. That data has been available since the early 2000s. The insulation industry has not disputed it. They have simply not referenced it. The fire test data is the second piece the industry prefers not to discuss in direct comparison. The ASTME 119 test is the standard fire resistance test for building elements in North America. It applies a furnace temperature curve that reaches over 1,000 degrees Fahrenheit over a 2-hour period, and measures how long the test specimen maintains structural integrity and thermal separation. A standard wood frame wall with fiberglass insulation fails this test in approximately 60 minutes. A plastered straw bale wall, tested under the same protocol by Intertek, achieved a 2-hour rating. The test was conducted. The number is public. You can look it up. It changes nothing in the standard building code process because the code is designed around a product that failed half as well. In the United Kingdom, a structural engineer named Barbara Jones spent 20 years testing and documenting straw bale construction in a climate that presents more moisture challenges than the American Southwest. Her monitored structures showed no structural degradation, no moisture accumulation, and thermal performance matching the laboratory predictions over timeframes extending into decades. Her technical documentation became the foundation for the inclusion of straw bale in the United Kingdom's green building standards. In France, straw bale is now incorporated into national building standards with defined technical specifications. Not an appendix, not optional. A recognized construction method with codified design rules. In France, you can build a straw bale house and get a standard mortgage to finance it. The data required to achieve this was the same data that has been sitting in American testing files for 20 years. And then there is the code battle itself, which is not a vindication story, as much as it is a documentation of exactly how difficult it is to change a system once it has decided what it knows. David Eisenberg, a building codes expert at the Development Center for Appropriate Technology in Tucson, spent more than a decade working within the International Code Council process to get Appendix S into the International Residential Code. The process required repeated fire tests, structural tests, seismic tests, moisture tests, and engineering review. Not because the data was lacking, but because the committee process is designed to require extensive documentation for anything outside its existing categories. The tests passed, every one of them. The data was submitted, the arguments were made. And in 2015, 125 years after the first straw bale house was built in Nebraska, the code caught up with the reality, partially in an appendix, that most jurisdictions have not adopted. The vindication exists. It's thorough. It is federally documented. And it changes almost nothing, because the systems that keep straw bale out of mainstream construction operate at a layer below the data. But here is what those systems do not control. In 2013, in the city of Leeds, in northern England, a group of residents completed the first affordable straw bale co-housing development in the world. 20 homes, mixed income, built with community labor. The project used straw bale infill walls in a structural timber frame. The insulation cost was a fraction of conventional. The embodied energy of the construction was roughly 1/10 of standard. The homes were certified to the Passive House Standard, the most rigorous voluntary building energy standard in Europe, meaning they use roughly 80% less heating energy than an equivalent conventionally built house. The system said straw bale was fringe. They built a neighborhood with it and let the numbers make the argument. In Arizona, New Mexico, and Colorado, the tradition of the bale raising has become a fixture in the natural building community. A bale raising is exactly what it sounds like. A group of people, often 30 to 50, shows up on a Saturday morning to stack a building. No construction experience required. The bales are large, awkward, and light enough that 2 people can handle them easily. They stack like bricks, offsetting each course, with rebar or bamboo stakes driven through to pin them together. By afternoon, all 4 walls of a modest structure are standing and pinned, ready for the first coat of plaster the following weekend. The material costs for a 12 by 24 foot workshop with plastered straw bale walls run between $300 and $900 for the bales at current prices. That is the insulation for an entire structure, in an afternoon for less than a single night of emergency plumbing repair. The people building these structures are not professional contractors. They are homesteaders, off-grid builders, owner builders who read what the industry does not teach and decided to test it themselves. And what they discovered is what the Nebraska settlers discovered in 1886. The complexity in straw bale construction is not in the construction, it is in the permitting, which means the barrier is not knowledge, it is not skill, it is not money. It is the distance between what the testing data says and what the system allows. That distance is maintained deliberately by people who generate $9.7 billion a year selling you an alternative that performs worse. A homeowner in California, which adopted straw bale into its residential code in 2009, can build a straw bale workshop on their property with a permit the county already knows how to process. A homeowner in most American counties cannot, because their jurisdiction has not adopted Appendix S. The underlying physics is identical in both places. The straw grows in both places. The fire test passed in both places. In one place, the system allows it. In the other, it does not. The Burke House in Alliance, Nebraska was built in 1903, the year of the Wright brothers' first flight, a year in which no one in America had a motorized vehicle in their household, and most homes were lit by kerosene. The house is still standing. The walls still insulate. The straw inside them has not degraded. The plaster has been maintained, as all plaster must be maintained, but the material doing the thermal work is exactly what it was when the house was built. 121 years of Nebraska winters at -30. 121 years of summers at 100 degrees. And the walls are still holding. The fiberglass installed in the first American houses to use it in the 1940s has been replaced. More than once. The product that was sold as the solution is sitting in landfills. The pink rolls have become pink-tinged garbage. The industry that made them charges for the next set. Owens Corning generated $9.7 billion in revenue last year. Not in 121 years. Last year. From a product that degrades and needs replacement, in a building stock that replaces it on schedule. The straw in the Burke House has been growing in Nebraska fields every year since 1903. It grows back whether you use it or not. It is sitting in fields right now, some of it being baled for animal bedding, some of it being burned for disposal. None of it, effectively none of it, being pressed into walls that would outperform what the industry sells you. The question is not whether the technology works. The testing established that. The question is not whether it is safe. The fire data established that. The question is not whether it is affordable. The arithmetic establishes that. The question is what you do now that you know it exists. There are 3 more systems on this channel that the industry has spent decades making invisible. Subscribe if you want to find the next one. It covers a building material that lasts 40 times longer than what you are probably using right now. The people who profit from the shorter version are counting on you not watching it.